Thank you very much for the nice introduction. It is truly an honor to be able to talk in front of expert in modularity. And I hope I can stir up some discussion, okay? Because I'm bringing another dimension of complexity in the modular design. And I hope I can sort of stimulate your thinking. I was introduced, but briefly, I did my career working on requirement engineering. I don't know if you know PSL, PSA, that's a very classic requirement engineering method and tool. And that's in 70s and early 80s. Okay? And at that time, we developed meta-programming and meta-modeling concept. And PSL was defined using meta approach. And in fact, we defined many modeling languages using meta approach at that time, already late 70s and early 80s. And then I moved to Belco and Bell Lab, started looking into software reuse. And certainly, in software reuse, modularity is a major concern. How we can actually reuse, develop modules that can be reused. Okay? So with that experience, I moved to SEI and started working on domain analysis. So feature-oriented domain analysis, known as FODA, was developed in 1990. And since that time, it has been widely used in product line engineering community. And then I'm still continuing my research on that. So I guess the right point to start with is to look back the definition of modularity. This is actually Wikipedia definition. So modularity is the degree to which a system's component may be separated and recombined. And very simple. But simple doesn't mean that it's easy. So, especially in the context of product line engineering, it's even more complex. So we like to have modules that are highly cohesive and loosely coupled. That's the goal. That's what we like to achieve through modularity. But nowadays, we are in this context. These engines show the reality in software development. So we are not developing a system for a single application. We are developing systems, software systems, for a family of products. Okay? And here, modularity becomes even more important. And how do we divide that is an issue. Let me briefly look at traditional software engineering. You all know. And typically, people depict this in V model. Okay? Requirement engineering, design, coding, unit testing, integration, and so on. But in my view, that was derived from hardware engineering concept. I think this is really bad model to follow in software. Okay? And because, but with that, V model, the way engineers are trained is that as long as they develop software that can satisfy requirement, which is defined for a single system, designers think that their job is done. Okay? But what happens in software engineering? Okay? We keep adding new functions, okay? Removing existing functions, changing functions, in addition to correcting errors and improving performance. Okay? So we need to build softness into software. Okay? And the V model we saw doesn't reflect that issue in the process. Okay? So the way we build a family of systems is basically copy and modify. Okay? So we, starting from product 1, we copy and modify and produce product 2, and so on. This continues. And there is a proliferation of versions from this approach. Okay? And, gradually design structure decay, okay? And code becomes spaghetti code. There are many, often we find unused code. I work a lot with industry people, and we analyze the software. We are sure that the codes are not executed. Okay? But if we suggest them to remove, they said, no, leave it, leave it there. Okay? I don't want to be responsible. Okay? That's the attitude. Okay? So software become, complex. Become with the spaghetti code as we evolve this software. Okay? So software is developed like hardware development, and there is very little effort to build softness into software. Okay? Software needs to be soft, easy to adapt, okay, to changing requirement. Okay? So I often compare this with car manufacturing. Once we buy automobile, we don't change that to make a pickup truck. Okay? But in software, that's the reality. That's what's happening. We buy software, we develop a software, we gradually modify, evolve that, and after a while it becomes something else. Of course, there will be a lot of commonality, but we are evolving that. But with this traditional approach, we can no longer, react to this new environment. There is diverse market need. There is, time to market pressure is becoming shorter and shorter, and there is fierce feature competition. If you look at this handphone, almost every 6 months you see new model coming out with new features. Okay? And there is a fierce feature competition, and somehow we need to be able to address that. Copy and modify approach will no longer work in this environment. Okay? So softness includes many properties like maintainability, adaptability, portability, interoperability, reusability, and many other abilities. Okay? This is not orthogonal properties, but we should be able to have developed system with these kind of properties. There are already many engineering principles available, like modularity, which is the major topic here. So we like to develop modules that are highly cohesive, loosely coupled. Okay? That's modularity. Abstraction, layering, harnesses information hiding. Okay? That's a very important one in product line engineering. Okay? Program families concept has been already talked about in 70s, I believe. And there are many techniques like meta-programming, application generators, and aspect-oriented software development is another one that we can use. In fact, we experimented that in product line engineering. But critical thing is how do you know what to hide? Okay? So information hiding concept is very, very good. That's, I think, fundamental engineering principles in product line engineering. But how do you know what to hide? Okay? So according to Parnas's paper, it said that design distance that may change must be hidden, encapsulated in a module. That's basically what it is. And then how do you know what to hide? That's an issue. So there comes product line engineering concept. And in my view, product line engineering concept is basically building softness into software so that it can be reused, easily adapted in developing new products. And this picture may depict the concept. And when we look at the market orientation is very important here. Okay? We look at the market. And there may be some market segment with different architectures. So we identify some common architectures and the component that can be plugged in. And obviously, we don't just plug in. We may have to do adaptation. And but we like to have the adaptation being done isolated in a module, not spread across all these different components. Yeah, I think that's the key. Yeah? So architecture and component is the major sort of domain-oriented architecture and component are the major artifact that we like to produce. So this is a sort of traditional approach, but with a product line approach, we like to have this happen. Yeah? So we like to have this common architecture for a domain, and that serves as a context for integrating various components that may have to be adapted. Okay? So that's basically what we are aiming for in product line engineering. Okay? So what is the technical core in this product line approach? The core is commonality and variability analysis. So we look at the market, or family of systems, and identify functional commonality and variability. Okay? And model that commonality and variability, and based on that model, we derive architecture, which serves as a bone structure for integrating component. And this architecture will have variation point at which various variant can be bound. Okay? So commonality, variability, architecture, variation point, and variant, those are the major technical core in product line engineering. Okay? And the variability, we like to hide variability in a module, basically applying information hiding concept. So what to hide in a module can be found through this commonality and variability analysis. Okay? So we will see various dimensions at which we need to explore variability and commonality. Okay? So that's technical core. So at least we need to look at variability in three perspectives. Okay? Functional variability, contextual variability, context in which a system is deployed. Okay? Contextual variability, binding time variability. Some of the features may be bound at compile time, some may be bound at runtime. Okay? So we need to look at those. So functional and contextual variability, and if we look at here, compile time binding, installation time binding, feature may be bound at installation time, or it may be bound during runtime. So we need to look at these dimensions. Okay, so functional variability is typically captured using something that we call feature model. So this feature model was developed when I was at SEI, Software Engineering Institute. And this was published in 1990 as a technical paper at SEI. And then there was very few citations for 10 years. And then since after 10 years, the citations sort of shoot up, and I think the citation is now close to 3,000 at this point. So a lot of people are interested in feature modeling, and a lot of researches are going on in the on how we can actually use this, how we do formal analysis, and so on. Yeah? So this is very simple model. You know. Commonality being captured in this way. This circular one indicate optional one, and this one, half circle, indicate variability, you know, alternatives, basically. And then we can add rules, composition rules like requires and mutual exclusion and so on. It's a very simple concept. So maybe people with a high school degree can understand what's going on. And I see various use of this model nowadays. And many companies I saw are using this to manage configuration. That's probably most widely used application area. And then recently I saw a company who manage rights, okay? Because nowadays we often use off-the-shelf code or open source and so on, and legal issue is very important. Okay? So for each and every features, they indicate whether this implementation comes from, say, open source, or comes from, you know, off-the-shelf source, or whether it is developed, and so on. So right management is something that I saw new application of this. But anyhow, this has been widely used. So this is typically used to capture functional variability and also non-functional attribute. Okay? So we can see commonality and variability, and by looking at here, we know we can easily find what feature need to be encapsulated, okay? By looking at this. Okay? So, for example, here, this is an example of elevator control system, and the position control. There are many different methods we can employ. We can use. And by looking at this, we know that this needs to be encapsulated. And you know, that's how this is being widely used to come up with modules. Contextual variability is very important. Understanding that is very important. Okay? So different operating environment, different legal and cultural constraints. Okay? Especially now we are, you know, developing these systems for global market. Okay? So we should be really aware of these legal issues, cultural issues, and different marketing strategy. This is also very important. Okay? So one way to, suppose we are developing some system, and one way to market is, you know, we package only core features, okay? And then sell that market at a very low price, so that, you know, the buyers can easily afford. And then we can gradually have them increase the number of features. That's one strategy that we can use. And if that is the marketing strategy, then engineering should be done to be able to support marketing strategy. Okay? So this is, again, something that we need to think about. Different and evolving market need. So market, continuously changes, evolves, and we need to understand evolution of these markets. Dynamically changing user context. All this we need to understand. And from my experience, that contextual variability really drives in the way we design, in the way we architecture. And one example is, say, fresh memory. Fresh memory, if it is used in a computer like this one, okay, and another usage might be USB drive. Okay? USB drive can be pulled out by the user anytime, okay? Whereas the USB fresh memory built into used inside this PC cannot be pulled out, so update rate can be slow, whereas USB drive, update rate should be very high. Okay? So with the simple one, architecture can be different. In fact, quite different if you look at the actual software. Okay? So this contextual variability is very important to understand. So one example is elevator control system. Okay? Elevator used in apartment, passenger elevator, okay? Used in hospital, okay? And elevator used in, for the flight. Okay? Very different engineering. Okay? And although it does basically same functionality, okay? Quality attributes are all different here. Okay? So that's contextual variability. Now we need to look at binding time variability. So suppose we have these features that we like to package and sell. Okay? And now we need to think about how we are going to package this. Okay? So when these features will be included and need to be decided. Okay? Will that be included during the asset development time, okay? Or pre-operation time, installation time, or operation time, run time? And we need to decide that. And then even if some features are already included in the product that we sell, we may turn that feature off, make them not available. Okay? Until, say, they pay money, for example. Okay? So we can turn that features off. Okay? So when they will be included, when they will be made available, are the different issues. Okay? So we need to think about those. Okay? So that's sort of a binding time variability issues. And all these decisions affect the way we engineer software. Okay? So basically usage context here drives a definition of this quality attribute, okay? Quality attribute. And from this we can identify functional capability features. Okay? And these capability features will be implemented by various domain design features. Domain and implementation techniques are something that we need. And how we actually combine these functional features, driven by this quality attribute. Okay? And which design feature we are going to select, again, decided by this quality attribute and usage context parameters. So now we need to look at this problem space and solution space. Solution space. Here, what I mean by operating environment is various devices or things that we need to select. Okay? So this is actually system perspective. Okay? So if this is a software capability, that software function may be encapsulated or may have to interface with external entities. Okay? That's what I mean by operating environment here. Okay? So various devices and maybe computing platform are all operating environment here. Okay? So we need to carefully analyze problem space in terms of goals, usage context, and quality attribute. From goals, we can derive capability or functional features. Okay? Usage context, okay? Usually we can derive operating environmental entities like devices and platforms and so on. Okay? From the quality attribute, we can have derive design features. Okay? So from this analysis, we build various component and architectures. Okay? So development roughly goes in this way. It's certainly not waterfall type approach. Okay, there will be iterations. Okay? Just to simplify this, iterations. But we define the goals, objectives, okay, in terms of features. Okay? So that's the beginning of feature modeling. And the usage context. From this, we come up with quality attribute. Okay? And we do feature modeling. And then solution space, we further refine these feature models, considering the features we identified from this and quality attribute. Okay? So we define this feature model, and based on that, we develop various product line artifact that we can use. Okay. So we will use elevator system. So while we are defining the goals, okay, we can say move object between different floors of a building in an efficient way. And there will be many ways. We can use escalator or elevator. But if we further define this one, move object between different floors of a building with a minimum usage of space, then certainly this will not probably be the choice. Okay? So we define this and then come up with sort of usage context features. Okay? So elevator control system product line, usage context, passenger elevators, freight elevators, passenger elevators, hospital use, apartment use, skyscraper, and so on. Okay? So that there will be different usage, and then from different usage, we can identify important quality attribute. Okay? Important quality attribute. Okay? So quality attribute here might be usability. There are many alternatives. Okay? And these are all optional features. Okay? And smooth and comfortable run, freight damage prevention. There may be many features. For the freight elevator, we wanted to keep the elevator balanced. Okay? To prevent freight to be from damage. So with that, we can have mapping for the passenger elevator. What are the important quality attributes and so on. for each usage context of the product. And then we come up with solution space features. So here, car call handling, elevator air conditioner control, all those things. Medical emergency for the elevator in the hospital. So we can have this solution space features. And again, we can have a mapping between these solution space features and usage context. So solutions space feature and qualitative mapping. So we use this convention: strongly support, weakly support, hot break, which is typically used by the researchers in this requirement engineering, object-oriented, goal-oriented requirement engineering community. So from those, we can construct a feature model, capability feature model like this. So here, driving service, passenger, and here maintenance, VIP driving, all these different driving mode we can identify. And call handling, whole call handling, car call handling, and there are nowadays call canceling features, which is optional one. So call cancellation and so on. Door control, and speed, low speed, normal speed, high speed, and so on. So we can identify capability features and the various operating environment features. Like here, real-time operating system, which operating system are we going to use? Position sensors, absolute position, relative position. There are many ways of deciding where the elevator is, and so we can identify those. Communication interface. So, and we can come down to design features. There are many design alternatives that we can think about and model them. So position control, and there are various techniques for identifying positions, speed profile, leveling profile, runtime profile, load compensation. This is included in a very high-end elevator systems. So there can be many design features, but what to use, which one to use, really depends on the usage context and quality attributes that are required. So that's, but when we develop component, we need to encapsulate this variability inside module. So this clearly show what to hide in the module. Again, mapping between capability feature and quality attribute and so on. So when we configure products, we can basically use this mapping table to configure and select features that we need. So that's the dimension of variability in product line engineering that we explore typically. And now feature-oriented development is something that I'm working on to develop a methodology to support development of software, starting from feature modeling and so on. So we have seen how we can construct this feature model here. And with that, we develop various architecture models. At least in my method, we look at 4 different architectures. One is conceptual architecture, which is basically to show functional structure of system. Okay? That's conceptual architecture here. Process architecture is to show concurrency. Okay? So we identify concurrent processes, how they interface each other. And then deployment architecture. And this is modular architecture. Okay? Modular architecture. So we look at those. And in some domains, I often find that we can actually generate these applications with sort of syntactic coating of this feature model to define domain-specific language. Okay? And then that generator use this architecture and component to instantiate applications. And in that way, we can produce more quality-oriented products. Okay? Many application generators, without this, okay, often generate very low performance applications, but with this, we can often create efficient applications. Okay. So methodology basically goes this way. We do market analysis and product planning. Okay, is done at front. Okay. And then based on that, we do feature modeling. So I explained the details on how we do feature modeling, but we do feature modeling here. Based on that, we do architecture modeling and design object modeling. This design object modeling basically derived from feature model. We derive object from features, and then architecture modeling, we need to consider various quality attributes. Okay? So there is no magic of going from here to there. Okay? Expert knowledge are needed there. And then we do architecture refinement and the component design. Okay, so using these elevator control systems, this is elevator control system is basically feedback control system. Okay? So the elevator control software basically use these signals from various devices, and then you send out output signals to various hardware component attached to it. Okay? So this is context diagram, and as you can see, we have this notation. These are variability, okay, variable component. Okay? These are variable component. Okay? This is again variable component. Okay? So if car call cancellation is included, then this component will be there. Okay? So this indicates variability. Context, basically context diagram. Okay? And then we do market analysis, identify various features for the domain. Suppose we are aiming for this high-rise office, general hospital, and apartment building. And then we do market analysis, identify various features that are needed. Okay? And that's the beginning. Okay? And then we define further these features using the approach that I already explained, okay? Object analysis and all those things. Okay? And then we have this capability feature here. That's basically functionality there. And then operating environment, that's various devices this target system interface with. Okay? And then these are the sort of implementation-oriented design technologies. Okay? So we divided that into two categories. One is domain technology, the other one is implementation technique. These are more generic ones that can be used outside the domain, whereas these are more domain-oriented techniques, like position control. There are many patented method here. Okay? So that's sort of domain technologies. Okay? So once we have that, then we do architecture design here. Okay? So we have this various car call handler, cage operation manager, safety manager, and so on, scheduler. We have a set of guidelines based on which we can derive various objects. Okay? So if we look at the feature model, those features at the toward the top of feature model tend to become the behavior hiding object. Okay? So it can be global behavior hiding object, local behavior hiding object. So as you can see here, we are sort of structuring object. Okay? So we may have global controller monitoring the global state of the target system. That elevator system is elevator software is trying to control, which is basically elevator hardware. Okay? So that's sort of a global behavior hiding module. But local behavior hiding module is like controlling motors, okay? Controlling doors. Okay? That should work in harmony with global behavior hiding module. Okay? So from this, we have guidelines on how we can actually derive various objects from feature model by hiding variations. That's important. Okay? We like to encapsulate variations in object. Okay? So there are couple of general engineering principles we use. I only listed a few here, but so objects are derived from domain model and feature model. Okay? So we use both. I didn't show domain model, but we use both domain model and feature model to derive objects. Okay? And we like to separate behavior from computational element. Okay? And of course, we like to also separate interface. Okay? I didn't write here, but separation of a behavior computation interface, pretty much like MVC model. Okay? So we do that. And this behavior is further defined into global behavior and local behavior. Okay? And there can be a network of behavior sort of hierarchy. Okay? So that's what we do. And we like to generate controller code from behavior specification. So we use, for example, state chart and various other techniques to define behavior, specify behavior, and then generate code. And this behavior specification is also parameterized. So when we select features, this can be instantiated, and we basically generate code out of specification. Yeah? One of the reasons why we do is we have a simulator that can simulate behavioral specifications, so we can debug early on. And once we debug, we might as well generate code. Okay? So that's what we do. And postponement of context binding as much as we can. We like to postpone. Variability defined in terms of variation point and variant, as I said earlier. Okay? So we have this variation point, and that variation point essentially encapsulates variations. And these are variations, okay? Variants. So that's general principles. I will skip that in the interest of time. Okay? And then, so here, interaction between external object and other part of the mediated by adapters. So we have this, we use adapters, various proxies, factories, like we all do in object-oriented, software development. We like to use that, those mechanisms to hide variations, variabilities. So we, as you can see here from this feature model, we can come up with this object model. Okay? And since this shows variabilities, in my view, we can more easily identify design object that can be reused. Because we know the variations, and we can sort of encapsulate that variations. But with typically many industry people use these use cases, okay? And from the use case they derive object, but a use case defined for a single application do not have variability. Okay? So in my view, what I observe typically is that object derived from use case do not have much reusability unless designer really pay attention to making that component object reusable. Okay? Whereas here we know the scope of variation, and with that knowledge, we can come up with better, more reusable object structure. Okay? And then here, so for the service features, we define that as a containment of behavior. Okay? So for example, here, emergency handling, this is specification of emergency control, and this state chart is sort of parameterized. Okay? So once feature is selected, and we can easily instantiate. What we found is that in some countries, when emergency happens in the building, okay, elevator must move to the closest floor, and some country requires that door need to remain open while emergency situation continues. Whereas in other countries, they require that doors be closed so that no one can jump in elevator. Okay? So different, and we need to be able to support that. So that's some parameterization to support that. Okay? And then we can simulate and generate code out of that. Okay? This is the containment of service features as a coordinator of contained features. So here there are two features, okay? And this one sort of coordinate. Okay? This one is the coordinator of various modes. So for example, elevator it can be in service mode, and then it can go into maintenance mode. Okay? When the elevator is in the maintenance mode, doors typically remain open, and the maintainer can stop anywhere in the building. Okay? So there is quite different operating mode. Okay? And we need to somehow be able to change from this mode to the other. Okay? If there is anything that needs to be done before transition happens, okay, this coordinator will do that. Okay? So we derive this coordinator from this, and then this is various mode controllers. Okay? So that's somewhat complex, but that's how we model in using a state chart. Okay. Okay. So computational component like generating speed profiles. Okay? That's basically computation intensive one. And we separate computational one from behavioral one because computational component rarely change. Okay? And once that component is debugged, okay, usually that it becomes very stable component. Whereas behavioral one, when we make modifications, we need to verify that the modification is correct. So that's why we use specification technique and separate computational one from the behavioral component, okay? So that we can focus on verifying control ones. Okay? And operating environment features as a containment of external object. And here, position sensors. There are many sensors. There are sensors for safety, and there can be many alternative sensors that we can use. Again, this one encapsulates that through adapters. Okay? So we use all these object-oriented, patterns that design patterns that we have. Again, this is alternatives when we have this optional ones, alternative ones. Yeah? We have this to hide that and bind that. So this will be the variation point. This will be variant. Okay? So this will be plugged in a elevator control driving service, and these are the variant that can be put into. So based on that idea, we can have this object model with various variabilities. Okay? These alternatives, optional ones, and so on. Okay? And so this will work as a variation point, okay? Where these are variant. Okay? And then from that feature model, we do binding analysis. Binding analysis has to do with how we can put this object together in a component. Okay? So tightly coupled object may have to be put into same component. Okay? So we do this sort of coupling analysis, okay? And then suggest binding units. Okay? So like this. Okay? This is feature model, and this is a sort of shrinked feature model. So all the features that can be put into same component are indicated by this one. Okay? So this one. So this provide variation point for that object, for that component. Okay? And this is variant. Okay? So we have modified design object model. And then we do architecture refinement, Okay? So for the elevator control systems, we have a distributed model and also centralized controller. Okay? And so we can have this, here scheduler and service manager being being executed on different computer, whereas we can have all of them on the same computer as one process. Okay? So there are alternatives, alternative architecture that we can support. Okay? So we use this MBC model for each to design each process here. Each process is designed basically using this MBC model. So we have this interface, controller, computational one, data manager, and so on. Yeah? Now, when we design this controller part, depending on the characteristics of application that we develop, we have various models. Okay? Currently we support 4 different models. One is sort of decision table-based model. Okay? Another one is a state-based model, workflow-based model, user interaction-based model. Okay? User interaction-based models are typically for game softwares. Game software, it's very much user interaction-oriented, and we can define interaction model and generate code. Okay? And then the reusable component can be plugged in the model. Okay? So we have various models and tool support. So elevator control system is sort of a state-based system. So we have this state chart usage. Okay? And also for the deployment, we can easily change deployment architecture. Okay? So once we have deployment specification done, and using that, we can very easily distribute, and there will be different connectors integrated to support communications. So once we have that, then we can basically generate or instantiate applications by selecting architecture, and if necessary, we need to do some code adaptation. And we select these features many different ways, okay? And then by selecting these features, we can basically instantiate architectures and generate some controller software. Well, I'm running out of time, so variability is achieved through product line architecture, variation point made at the architecture, and then various variant. Okay? So variabilities are encapsulated in a module, basically using information hiding concept. And there are many patterns that are based on information hiding concept, and we use that. Okay? And various variability mechanisms are used, like, of course, inheritance, macro processing, generators. Where appropriate, we use different techniques. Okay? So the technical core here in product line engineering, we have this, product line architecture with variability, with the variation point and variant. And in order to be able to find those variation point and variant, we do commonality analysis, which are typically done using feature model. Okay? So I hope I didn't confuse you too much. Thank you for listening.
Thank you for your great talk. We have several minutes for question and answer. Okay, please.
So this is Eric Ernst. I'd like to ask you, if you have a system that is built according to these feature diagrams, it's very likely that you could generate a few billion variants and maybe have 123 products using them. And now somebody finds a bug and changes one file. Do you need to make one test or 123 tests or a billion tests?
That's a good point, actually. Yeah, so on the first point, actually there is feature explosion problems can happen. I heard that some domains like automobile has over 4,000 features, something like that. And certainly we need to apply here engineering principles like separation of concerns and so on to simplify. But think about this. You know, domain is that complex. Suppose that knowledge is all in human mind, mind. How are you going to manage that complexity? Somehow we need to codify that knowledge and be able to use that knowledge when we design. We need to be able to analyze consistencies and all those things. Unless we put that down, create model, it will be almost impossible to do. So certainly, when we make a feature model, certainly we need to apply separation of concern. Again, modularity here, concept of modularity, how we are going to modularize. Certainly for the large complex domain, you don't probably throw one single 4,000 feature, diagram with 4,000 features. That's too complex. Certainly you need to modularize. Testing is an issue, actually. It has variability built into, and that's why I separate behavioral things from computational one. And for the behavioral one, once instantiated, we like to be able to analyze and verify that specification is correct. So that's the approach we are taking. Yeah, that's good research area, actually. Yeah.
So I have always wondered, you make this feature model up front and you have a lot of the variability explicit, but it changes over time. So you also want to maybe remove some of these features because they are not relevant to the market anymore. But now what you have shown us also were all these models where you reference all these features. So have you any thoughts on when basically I want to remove them and I don't want to have like a dead code model? Okay.
Okay. Yeah, that's a good question. Yeah. So certainly, feature model will not remain static. Okay. Our market is very dynamic, and features need to evolve. But when you have those feature model and variabilities sort of confined, isolated, okay, and usually variation happens within that scope. Okay? So I think what's important is to abstract and encapsulate. Okay? So in my experience, usually that variation happens within that scope. Okay? Certainly, if it changes drastically, I mean, there is no.
Hi. Development the product line seems quite expensive. If in particular, it's very large. So it seems that it's only possible for large enterprise. So my question is, how do you guide developers to build a realistic product line?
Okay.
Do you guide us to first develop a small one and expand it gradually? But if it's true, I think the crucial key thing to develop that product line is a linguistic mechanism for software evolution.
Right. Yeah, actually, I got that similar question, often. But I think product line approach can be applied to in any software engineering environment. As I said from the beginning, I show a big example and complex feature model, but when you do, say, for example, agile development, okay, you develop some software, okay, and suppose you are developing a similar software, okay, are you going to do in a same agile way? Perhaps you want to use what you have learned previously, okay? So actually what this one is, how we accumulate, okay, our development knowledge, okay? So basically feature model is domain knowledge that typically this expert has. Okay? They know what features are, how to integrate those features, and they have this expert knowledge. So we like to be able to codify knowledge that we gain and then apply that continuously. Okay? So that we can, again, we are software engineers. We like to develop soft software that can be easily adapted. Okay? How do you do that? I mean, you need to be able to codify your domain knowledge and variabilities in a model and reapply that. So feature model may start very small and then it can grow. Okay? If you adopt that from the beginning of some project. Okay? But certainly once you develop a system, soon after you have to modify. Okay? You add new things, you remove certain things, and that happens. Okay? That knowledge needs to be codified. Okay? So you can start small, but you can grow into real product line organization. Okay?
But usually it's hard to start small because you already have a huge product, and then you want to extract or do a reactive approach, and then you already have all the problems.
Sure, so. Yeah, that's actually a practical problem, and many industry, has that strong need for that. So there are extractive approaches. Okay? So from the products you have already, okay? And you extract feature model out of that, okay? And then re-engineer existing one, and that there are some approach to doing that. We call extractive approach to product line engineering. Yes.
Okay. We have a small gift for Professor Kang. This gift is the Hakata doll, Japanese traditional doll in Fukuoka locals.
Thank you.